In this video, we're going to look at Section 3 of the 2018 April exam for Math 121. The scenario is that there's a pile of toonies in the Canadian economy, 200 million, and when we look at that, it's going to be divided up into the 200 million total, of which we can categorize each toonie as either old or new. And between those two groups, that defines the 200 million. Now, what we have originally is a bunch of old coins, all of them being the old design, and then gradually as toonies are deposited at the bank replaces any old coins they get with the new version. I would say the major tip in this question is just not to overthink it. Because this is a new model, the question walks you through the stages. So we define n as the number of new toonies in circulation at a certain day t. So if n is the number of new coins, how many old coins are there? Well, the old plus the new adds up to 200, and so the old is simply going to be 200 minus n. And if you like, n of t. That looks like a 0, so we'll call it old of t. That's it. So at any point in time, if someone tells us there's 50 million new coins, well, that means there's 200 minus 50, 150 million old coins. Next up, if n is the number of new coins in circulation, what fraction of the total circulation is in old coins? Well, the fraction is going to equal our old over the total, and that's 200 minus n of t all over the actual total population of coins, which is 200. Now, why is that fraction important? Because if we know the number of new coins, and we know on a given day 0.5 million toonies are going to be deposited, then we know the fraction, all the old coins in that group are going to get replaced with new coins. So knowing n of t, how many old coins will be deposited? So there's 0.5 million deposited. That's all toonies. However, the fraction of those that are going to be old is exactly what we found in the previous question. So the number of old toonies deposited is going to be 200 minus n over 200, that fraction, times the rate, 0.5 million. At the end of the day, this is the rate per unit time, because this is per day, so we could actually write this out as the change in the number of new coins, because that's what this number defines. It's the number of old coins that comes in, and so it's also the number of new coins we get is going to be 200 minus n over 200, and that's per day, times 0.5. And then that is we're going to get that many changed times the number of days we do it, times delta t, bring the delta t to the other side, and all of a sudden we have something that looks like a derivative. We imagine delta t getting smaller and smaller. We get this expression, but everything on the right-hand side stays exactly the same. And that's it. This is the number of coins, new coins added to the pool per day. That matches perfectly with the units of our derivative. We can now work to solve our differential equation through the separation of variables. So we have our formula, which was 200 minus n all over 200, all times 0.5, and I'm going to bring this in as 100 minus 0.5 n all over 200, and the reason for that is it allows us to separate the n term, the numerator, nicely with the denominator. It's not the only way, but it seems like a reasonable starting place. So if we do that, we do our separate and integrate. Then we're going to get the numerator and the denominator on the left-hand side. And the right-hand side is going to stay as 1 over 200. And the dt here, we move up. It becomes that expression there. And then we integrate both sides. The right-hand side is the easier part. It's just 1 over 200 times t. The left-hand side is a logarithm. We have to be a little bit more careful with this one because the negative 0.5 has to show up as a constant outside as well. When we differentiate this, we would get a negative 0.5 popping out to cancel that. We need the negative 0.5 in the denominator there. And can't forget our plus c. So we've separated, and then we integrated, and now we're going to solve for n. So we're honing in on this. So the first thing is to get just the logarithm on the left-hand side, i.e. multiplying this up to the other side, pardon me. So we're going to have 0.5 over 200 times t, negative 0.5 over 200 times t, plus, I guess, negative minus 0.5c. And this is really what no one likes. So if we multiply this out, this will be in the bottom. This will be negative 1 over 400 when we're done. And the next step is then to get rid of the logarithm. We do that by taking an exponential of both sides. The entire left-hand side is going to be raised to e to that power. We'll do the same thing with the entire right-hand side. We just need to be careful with the power rules of that. The e and the logarithm cancel. And we get 100 minus 0.5 n's is equal to e to the negative 1 over 400 times t. You have to remember this is a coefficient, the t is just a multiplier, minus 0.5c. But that we can break into two components. Again, this is pretty familiar stuff to what we've done with other differential equations now. And the next step is to get rid of these absolute values and to get rid of this exponential here. We just give this a name. We call it a, and we get rid of the absolute value signs by saying, well, whatever sign this needs to be, it's currently positive, but we want to get rid of the absolute values, which might be negative, so we'll just do all that in one step. And we keep going. We get a e to the negative 1 over 400t. Keep focusing in on n. We get negative 0.5 n's is exactly what we had in the right-hand side, minus 100. And then we just divide through by negative 0.5. And what do we get? Negative 0.5. Oops, we're dividing by negative 0.5, which is multiplying by negative 2. Negative 1 over 400t. And we're dividing by negative 0.5, which is multiplying by negative 2, gives us plus 200 there. And what's the only other thing we knew? Oh, right, we can solve for a, actually, because we know that at the beginning of this whole experiment, the number of new coins at t equals 0 is none, because we have no new coins when we start this experiment. So we can sub that in. We get 0 equals negative 2a e to the 0 plus 200. E to the 0 is a lovely number. It's just 1. So this quickly turns into, let's bring that over, negative 2a, positive 2a equals 200. That means a equals 100. And we get our final solution by putting all of that together, these two expressions. N is equal to minus 2a's, so minus 200, e to the minus 1 over 400t, and then back on the main line, plus 200. That's the number of new coins in circulation in millions. All right, that's our solution. Finally, we can use that to make a prediction. How many days will it take for the proportion of new tunies in circulation to reach 90% of the total? Well, 90, this is a number. Our n is a numerical value, numbers of coins in millions. So if not the number of coins, it's 0.9 times 200 million, which is 180 million. if that's what we're looking for, we're going to set n equal to 180 and solve for t. So just squirt that up here. There's our formula. 180 is equal to negative 200 e to the negative 1 over 400t plus 200. And we start solving. I would bring this over. 200 e to the negative 1 over 400t is equal to, bring the 180 over, we just get 20. That gives us, we can divide through, e to the negative 1 over 400t is equal to 20 over 200, much better known as 0.1. Now we go the opposite direction from earlier, because we're trying to break into an exponential this time, so we slide a logarithm in front of these guys, and we get negative 1 over 400t is equal to ln of 0.1. And so t is equal to negative 400 times the ln of 0.1. That seems weird, it looks negative, but our ln of 0.1 will also be negative. We start reaching for that, type it into our calculator, and we get something around 460 days, or about a year and a half, a year and a third at this rate, to exchange all the old coins that are in there, sorry, not all, 90% of the old coins for new coins.